and welcome to my talk on chemical bonding. So my name is Leigh Jones. I'm a lecturer at the University of Wolverhampton. It's my pleasure to give you this Aspire to HE talk on chemical bonding. So what is chemical bonding? Well, it's incredibly important. That's what it is. Essentially, compounds, which are of course made up of different elements in different ratios, are held together by chemical bonds. Okay, so these two pictures here, for instance, on the left is aspirin, as I discussed previously in one of my other talks, is of course a pain relief medication. And this is actually the chemical makeup of it. It's just simply made up of carbon atoms, hydrogen atoms, and oxygen atoms in a specific shape or topology. These lines essentially just are basically chemical bonds. So, for instance, this carbon, which is an edge here, or this carbon here, is bound to another carbon here. This carbon here is bound to an oxygen here. So these are all chemical bonds. Likewise, on the right-hand side, an inorganic material is sodium chloride, or rock salt, or table salt as we call it. So essentially the sodium ions are the blue spheres and the chloride ions are the green spheres, and they're essentially linked together. And this is exactly how they are bound in the solid structure. And the bonds are just these lines connecting them together, as you can see. So, for instance, each sodium is surrounded by 1, 2, 3, 4, 5, and 6 chlorides, for instance, and likewise each chloride is surrounded by 6 sodiums. So we're going to look at what type of bonds that these different materials actually show. And what I'm going to show is that essentially aspirin, the organic molecule, has more covalent bonds, and the inorganic material in sodium chloride are more electrostatic, or what we call ionic bonds. But first of all, what is bonding? Essentially, without chemical bonds, the atoms would fly apart. They would not be held together, but they are held together by these strong chemical bonds. And there are different types, for instance, ionic, for instance, in sodium chloride. There are covalent bonds, for instance, in aspirin. And in real life, you don't get just one or the other. Bonding could be somewhere in between, for instance. It could be somewhere in between ionic and covalent. It really does depend on the atoms that are being joined together. Essentially, bonding is the interaction of what we call the valence electrons. Okay, so don't be worried about these words. Valence essentially is the outer electrons, so the ones furthest away from the nucleus, essentially, which is this black sphere here and the black sphere there. So essentially, you've got two atoms in this diagram moving together. Essentially, it's the valence electrons that are actually going to interact first with each other. What they actually do is that they will sort of swap or share electrons with each other, with the sole aim of having, in the end, a full valence shell. In other words, where all orbitals in that shell are actually full and nice and stable. Why is this? Well, essentially, when you have a full valence shell, you are nice and stable. There is no need for you to lose any of your electrons. So, for instance, in this diagram here, you've got a very basic diagram of neon. So the blue spheres are the electrons in the different shells. So you've got 2 in the first shell and then 8 in the next, okay, as you would. So of course those 8 electrons come from the 1s orbital and the 3p orbitals. Each orbital holds 2 electrons, remember, from your A levels. So that's neon, and this is why neon doesn't really do much in terms of reactivity. It's just a gas, an unreactive gas. Helium, likewise, very simple system, just the 2 valence electrons. I'm not willing to really lose either of those electrons. So these noble gases have full valence shells, and so they are unreactive and very stable. However, in chemical bonding, the electrons redistribute so that all atoms have a full valence shell. So in other words, other atoms do not have these full shells, therefore they are going to interact with different atoms to make a plethora of interesting materials. So what is a full valence shell? Essentially, you're obeying the octet rule, so the notion of electrons redistributing so that all atoms have a full valence shell. Okay, and the octet is the 8 electrons. So in other words, all you're trying to do is fill the s orbital and the 3p orbital. So in other words, a total of 4 orbitals, which means 4 times 2 is, of course, 8. So a configuration where an atom has 8 electrons in its valence shell is called the noble gas configuration. So in other words, a full valence shell can also be described as the noble gas configuration, and that's what they're striving to do. Let's look at oxygen, for instance. Now, on the left and on the right, essentially it's just an energy level diagram of the different shells, shells 1, 2, and 3, of course. In shell 1, you have the 1s orbital only. In shell 2, you have the 2s and the 2p. The 2p orbitals, as we know from A levels, are of a higher energy than the 2s. And then in shell 3 would be the 3s and the 3ps. Now, if you look at oxygen, because this is actually oxygen that we're looking at, we know that oxygen only has 8 valence electrons. So we simply put them into the different orbitals, as you can see. So the 1s is full, the 2s is full, and then one of the 2p's is full, and then the other two are only half full. Okay, so if we add these together, 1, 2, 3, 4, 5, 6, 7, and 8. Happy days. So how are we going to make this nice and stable? The only way we're going to make this nice and stable is by gaining 2 electrons, one in one of the p orbitals and one in the other 2p orbital. So these are the dark blue arrows here. So 2 more electrons are required to fill this valence shell. And this is why we have the oxide anion. It's a very, very common anion in chemistry. An anion just means a charged species, a negatively charged species. But because this has gained 2 electrons, of course, then we give it an O2 minus. Therefore, it's negatively charged. Therefore, it's an anion. If something was positively charged, we call it a cation, by the way. And I'll show you an example in a second. Okay, what about sulfur? This time, sulfur is a different atom, of course, different elements. It has 17 electrons. And we've again put them into the 1s, the 2s, the 2p, the 3s, and the 3p. And again, very similar to oxygen, one of the p orbitals is full and the other 2 are only half occupancy. So once again, to obtain a full octet shell here, then we only need 2 electrons. So in other words, the sulfur atom will take 2 electrons when it's interacting with another atom to become the sulfide, the S2 minus anion. Okay, so they're just 2 simple examples of how an atom can take electrons to give itself a full valence shell and become what we call an anion. Of course, if they need anion, if they're going to form anions, they're going to need cations. Anyway, we'll talk about that in a second. So the 2 most common types of bonding are covalent and ionic bonding. A covalent bond is essentially the sharing of one or more electrons. Okay, and so in other words, they share rather equally between the atoms. An ionic bond is where the sharing is not particularly good. One of the atoms is more greedy than the other, essentially, and so there's a full transfer of electrons, or maybe just one electron from one atom to the other. So this diagram at the bottom here shows you. So example A is a covalent interaction. So this X species here is interacting with Y. The dot is just an electron, as is this open dot here. They're coming towards each other, and lo and behold, they're forming a bond because they've got 2 electrons there. Okay, they're sharing those 2 electrons, and therefore they can fill that orbital essentially, and you've got a nice equal sharing, which means it's a covalent bond. A covalent bond has been formed. Ionic. So imagine the same 2 species here. Imagine this time the X species completely gave away its electron and gave it to Y. Therefore, X would be without an electron, Y would have 2. So in other words, Y would have a minus charge and X would have a plus charge. So we call this an electrostatic interaction, which is basically an ionic bond, okay, because ions are formed. So X would be your cation, Y would be your anion. So as I said, ionic bonding is the complete transfer of an electron from one atom to another. So of course you'd form a positive ion, which we call a cation, and a negative ion, which we call an anion, because of course the cation has lost an electron, the anion has gained an electron. And the attraction between the cation and the anion constitutes the bond, which is the electrostatic interaction. So this is a really specific example here. Sodium, we know, has only 1 valence electron. Okay, so look in your books to confirm that with yourselves. We know that chlorine has 7. So chlorine only needs 1 electron to obtain a full outer shell. In other words, it will. So the sodium has totally given the electron to the chloride to make it an anion, a chloride as we call it. And of course, the sodium is a cation. And this is essentially very true because we know that the bonding in sodium chloride is electrostatic, it is ionic. And as I discussed previously in the previous picture, the lattice is actually held together through the electrostatics of Na plus being attracted to Cl minus. Okay, so the different charges hold this system together in what we call an extended network. So the goal, of course, is to lose or gain enough electrons to achieve a full outer shell. So if we look at sodium chloride again, or sodium and chloride, yes, using the same type of energy level diagrams, here we've got sodium, look, we've got a 1 electron in the 3s orbital. And then if you look at chloride on the right hand side, that's got 7 electrons in the 3s, sorry, in the 3 shell, okay, in the third shell. So essentially, sodium will lose an electron, therefore it becomes full. So full n is equal to 2 shell. This will gain an electron here, which is the dark blue arrow here, and that's got a full n is equal to 3 shell. So they're both happy that we have obeyed the octet rule for both sodium and the chloride, giving you sodium chloride. And the last thing to think about really is if you look at sodium, it needs to lose 1 electron. The only other thing it could do, of course, is gain 7 electrons to fill the 3s and all the 3p's. But of course, that's a difficult route. That's not going to happen, okay? So you can use your chemical intuition to say, actually, no, sodium is more than likely to just lose the 1 electron to give itself the full shell 2 valence shell. So what about oxygen? Again, let's look at this. If you look at oxygen, again, it's got 1, 2, 3, 4, 5, 6, 7, 8, valence electrons. And of course, it's going to gain 2 electrons to become that O2 minus. Okay, so coming full circle. What about something a little bit more tricky? Essentially, some atoms will give more than 1 electron to more than 1 atom, or will give 1 electron to 1 atom and 1 to another. So if we think about magnesium, for instance, magnesium reacting with chlorine, okay, we know that magnesium has 2 valence electrons, so it needs to lose both of them. Imagine it's reacting with chlorine, though. Chlorine only needs the 1 electron. So of course, magnesium is going to give 1 to 1 chlorine and 1 to the other. Okay, therefore magnesium will become 2 plus, and each of the chlorides will become minus 1 each. And of course, they balance out because 2 plus minus 1 and minus 1 is 0. So there's an overall net charge. And that's why, essentially, magnesium chloride isn't MgCl, it's MgCl2, of course. So in other words, for every magnesium, there are 2 chlorides. Thank you very much.